Okay, welcome back. Last time we looked at our first example of projectile. Well, first of all, I guess I should say we learned the basics of projectile motion, what it is, and some key facts to know. And we also looked at one example where an object was projected horizontally. Now, in this video, we're going to look at two different examples in which objects are projected at an angle. Take the game of baseball. Let's say a baseball is hit with an initial speed of 40 meters per second at an angle of 33 degrees from the horizontal. We want to know three things. What's the maximum height of the baseball? What's the total time that the baseball is in the air? And what's the horizontal distance that it travels? So I'm going to put question marks by those right now. These are the things that we're looking for. Step one is to draw a picture and to label the directions that are positive. So here's my baseball. It's launched, it's hit at an angle of 40 degrees, 33 degrees. There we go. And that is done at an angle, or with an initial velocity of 40 meters per second. And it also has to label the positive directions. Again, this is kind of important because it determines whether certain numbers are going to be positive or negative. Let's just do our standard. X is positive to the right, Y is positive going up. Your next step after you make a really quick sketch is to write down the X and Y quantities separately. Remember that you can't mix X and Y quantities together. The equations, if you try and plug in both an X variable and a Y variable into the same equation, you're just going to get junk. Okay, the equation's not going to give you anything that matches reality. You'll get a number probably, but it won't be anything that would actually happen. Okay, so you can't mix those together. What we do need to remember, though, is we do need to remember one of the basic facts about projectile motion. Really, there's two of them. In projectile motion, which is a type of motion in which gravity is the only thing affecting the flight of the object, the projectile, we know the accelerations for any object in projectile motion. The acceleration in the x direction is 0 meters per second squared, and the acceleration in the y direction is either positive or negative 9.81 meters per second squared, depending on your axis. We know that the acceleration due to gravity is towards the Earth, so down in most cases. Since we said that y is positive going up and acceleration due to gravity points down, that means given our axis, the acceleration due to gravity should be negative 9.81 meters per second squared. Did it have to be? No. If I had made my axis so that y was positive in the downward direction, then this would become positive. But I didn't, so it's fine. You'll get the same exact answers either way. So it still looks like I don't know a lot of stuff. I suppose I know the angle here, 33 degrees. I don't have the initial or final velocities filled out, although I guess I do know that this baseball is eventually going to reach a peak. And we talked about how when we were talking about free fall, if you throw something straight up at the very peak of its motion, it's not moving in the y direction because it can't go up any farther and it hasn't started falling down yet, so it must not be moving. So Vy top must be 0. So it looks like there's 4 more things that I don't know, but I can determine them because I was given the initial velocity of the baseball and the angle it was launched at. Notice that the initial velocity of the baseball is not in the x or y direction. What that tells you is that we need to figure out the x and y components of that initial velocity, okay? Because it doesn't really matter what the initial velocity is if we don't know the x and y components. It could be whatever. What we're going to focus on is the x and y components, because then we can plug them in for our x and y tables, and we can use them in our x equations and our y equations. So we're going to use the reference table and its equations to figure out what the components are. Remember that in order to find an x component, all you need to do is take the magnitude of the vector and multiply by the cosine of the angle. So in our case, the vector that we're talking about is the initial velocity, and we're going to multiply by the cosine of the angle. Remember, theta is a symbol for angle. This ends up being 40 meters per second times the cosine of 33 degrees, and that turns out to be 33.55 meters per second. Now, because we know the initial velocity in the x direction, and we also know that the acceleration in the x direction is 0, that also tells me I also know the final velocity in the x direction. Because think about it. If there's no acceleration, that means that the velocity in the x direction can't change. So the final velocity in the x direction must be the same as the initial velocity in the x direction. So that's also 33.55 meters per second. In the y direction, I know that the equation for finding a y component is the original vector times sine of theta. So in this case, it's going to be the initial velocity times the sine of theta. And that would be 33, or I keep mixing up my 33s and 40s. 40 meters per second times the sine of 33 degrees. That is 21.79 meters per second. VFY is kind of implied to be the speed that the velocity that the baseball has in the y direction just before it hits the ground. Now again, if we think back to our free fall notes and video, there was a fact that we learned that if something lands at the same height that it was launched from, then upon just about hitting the ground, it's actually moving with the same velocity or the same speed, but in the opposite direction. So if this object initially was launched with a vertical velocity of 21.79 meters per second, right before it hits the ground, it's going to have that same speed, that same velocity, but just with the opposite sign. I shouldn't say the same velocity because it's the exact opposite velocity. So VFY is negative 21.79 meters per second. And if you don't remember that, you can go through and prove it. It just takes a little bit of math. Okay? So notice that we were given not a lot of information, just the initial velocity and the angle, but we were able to fill in almost everything on this entire table with just that info. The only things that we're looking for are the things that we were asked to find: the final distance, or the total horizontal distance, the maximum height, and the time that the ball was in the air. And notice also that nothing in these tables, none of these final answers have anything to do with 40 meters per second. That velocity was not in the x or y direction. Okay, this is why we learned about vectors in the first place. We learned about vectors in the first place so that we can do things like projectile motion, in which we need to separate variables into their x and y components. 40 was not in the x or y direction, therefore we break it into its x and y components, and then we use those instead of the 40. First question we're going to look at is the maximum height of the baseball. Okay, so maximum height, that's going to be dy max. One of the things you might notice is we don't know the total time that the baseball was in the air for yet. If you look at your kinematics equations, all of them have something to do with time, with the exception of this third one down here, vf squared equals vi squared plus 2ad. So what I'm going to do is I'm going to pick that equation, because otherwise if I tried to use an equation that had time in it, I probably wouldn't, I wouldn't be able to solve for the distance. I wouldn't be able to solve for the height, what I'm looking for. VFY squared equals VIY squared plus 2AY dy. Again, remember, F and Y and I and Y. The Y's are just subscripts. You don't even really need to put them, but it reminds me that I'm using the Y direction variables to make sure that I don't accidentally plug in an X variable. Let's see. I know, so for final velocity, notice we're looking for the maximum height. So really we're looking for the height as the ball goes from the ground, where it was hit, up until its maximum height. That kind of implies that this speed here, even though it says VFY, we're talking about the speed at the maximum height, the speed at the very top. Well, we know that that's 0. Okay, so I'm just going to plug in 0 for that. Don't get confused and think that you're looking for the max, that you're going to plug in actual VFY here. We're looking for the distance that the ball has moved from the time where it has an initial velocity to where its velocity is 0 in the y direction, which is at the maximum height. The initial velocity in the y direction is 21.79 meters per second. Don't forget the squared, plus 2 times negative 9.81 meters per second squared dy. 21.79 squared is 474.8041, but that's going to get subtracted to the other side, so I'm going to do negative 474.8041. 2 times negative 9.81 is negative 19.62 dy. I divide both sides by negative 19.62. And I end up with the maximum height, the height when the vertical velocity has gone down to 0, is 24.2 meters. Okay? Oh, that's not what I want. All right, total time in the air. There's really two ways to do this, and I will show you both. We have, since we're talking about, okay, so for the first part, we were talking about maximum height of the baseball. That was very clearly the y direction. For time, it's not really clear whether we should use the x or the y. A general hint is almost any time that you're looking for the time that something takes to happen and you've got two-dimensional motion, you're going to be looking at the y direction, okay? Because how high the ball is in the air really dictates how much time it's in the air for. So we're going to be looking at the y direction again. We've actually got this all the way filled out, so there's a couple different equations that we could use in the y direction, but we're going to use the one that's used most commonly. We are going to use it two different ways, though. We're going to look at this equation right here, the so-called Fiat equation, VF equals VI plus AT. There's two different ways you could use this. First, I'm going to do it this way. Let's say that, okay, you know the final velocity in the y direction, the final velocity right before the ball hits the ground again is negative 21.79 meters per second. The initial velocity was the same, just in the positive direction, okay? So the initial's in the positive direction, final's in the negative direction. That makes sense. The acceleration is negative 9.81 meters per second squared times t. If I go and solve for t, that means I need to get t by itself. First thing I'm going to do is subtract 21.79 to the other side. Be careful, it looks like that might cancel out, but it doesn't. Negative 21.79 minus 21.79 gives us negative 43.58. We then divide by 9.81 on both sides, and we get a time of 4.44 seconds. Okay, so that's if we remember that the final velocity right before the ball hits the ground is the same speed as the launch speed, but just in the opposite direction, so you put a negative sign on. There is another way to use this equation. You can use either one of these methods. What if instead we found the time that it takes the ball to go from its launch point up to where it has a velocity of 0 at the very top? That would make this 0. It makes our math a little tiny bit easier because it's easier when we can just deal with something that's 0. Everything else remains the same. This becomes negative 21.79 equals negative 9.81 t. Divide both sides by negative 9.81. And the time for the baseball to go from launch to the peak is 2.22 seconds. That's not everything you have to do, though. Remember that that is only the time to go from launch to peak. We need the total time, not just from launch to peak, from launch to landing. When we studied free fall, we talked about how objects take the same amount of time to go up as they do to come back down. So if I double this time, I get the 4.44 seconds that we had before. So either method is acceptable. Okay, they'll both give you the same thing. Last question, what's the horizontal distance traveled? Now we're talking about the x direction. There's only one equation I can use here because the acceleration in the x direction is 0. Notice that if I plugged a 0 into the kinematics equation or the third kinematics equation, I would end up with some variation on the final velocity equals the initial velocity, which is true in the x direction, but it doesn't help us solve for the distance. I need to use this second kinematics equation. Since the acceleration in the x direction is 0, this entire term cancels. The initial velocity in the x direction is 33.55 meters per second. The total time in the air is 4.44 seconds. Therefore, the distance traveled by this baseball is just under 150 meters. enough to be a home run in basically any major league park. Okay, now because this A canceled out, notice that we could have done something a little different. We could have even used this equation. The average speed in the x direction is just, since the velocity in the x direction doesn't change, it's just the 33.55 meters per second. I know that the time was 4.44 seconds. We get the exact same thing. So notice that this equation, in the absence of acceleration, reduces to this equation. They become the exact same thing. However, if an object is accelerating, we can't use this equation because it doesn't account for the acceleration. Okay, so most important thing, if you have an object getting launched at an angle, one of the very first things you do is figure out the x and y components of that initial velocity, and then you just treat it like any other problem. Okay, you plug those, you write those down in your tables, and then you use kinematics equations as necessary to find whatever you need. We'll do one more example, a little bit of a hypothetical question here. If we're going to launch an object, which of these will go farther? An object launched from the ground with an initial speed of 20 meters per second at an angle of 70 degrees from the horizontal, or an object launched from the ground with an initial speed of 20 meters per second at an angle of 20 degrees from the horizontal. So we're going to do both of these. One of these I'm going to walk you through, and then the other one I'm going to do very quickly on my own, quietly, and you can follow along or try it on your own as well. This will be the 70 degrees side. This will be the 20 degrees side. Very first thing I'm going to do, I'm going to narrate the 70 degree one. We're going to sketch. So we have an object that gets launched at an angle, or with a velocity of 20 meters per second at an angle of 70 degrees. Here's our axis. Okay. Very first thing I'm going to do is going to make a table just like we did before. Okay. These tables don't really change, so it's pretty easy to remember what you have to write down. In the other category, these aren't things in the x or y direction. We don't know the time, but we do know that the angle that the object gets launched at is 70 degrees. In the x direction, we might want to know the distance, we might want to know the initial velocity, we might want to know the final velocity, we might want to know the acceleration. There we go, hopefully that's focusing better. In the y direction, we might want to know the maximum height. We might want to know the initial velocity in the y direction, perhaps the y velocity at the very top of the flight, the final y velocity, and of course, the acceleration in the y direction. These are pretty standard, they don't really change. Now, based on the general facts that we know about projectile motion, we know the acceleration in both the x and y directions. In the x direction, the acceleration is always 0. Nothing's pushing or pulling it in the x direction. And in the y direction, since we said that the y direction was positive pointing upwards, acceleration due to gravity points downwards, the acceleration in the y direction must be negative 9.81 meters per second squared. We know that the velocity at the very top in the y direction was 0. Notice we don't say that the velocity is 0 in the x direction, because we know that this object is moving forward in the x direction, but since the acceleration in the x direction is 0, that means that the velocity in the x direction can't change. So make sure you're very clear on the fact that at the very peak, the object is still moving forward, it's just not moving up or down at that one instant. We don't know the horizontal distance. We don't necessarily know the maximum height. Those might be things that we find. Matter of fact, we are looking for which will go farther, so we're looking ultimately for dx. And before we did this, we probably should have talked about why this is kind of an interesting problem. If you launch something at a high angle, it should be in the air for a long time, but it's probably not moving forward very quickly, okay? It probably doesn't have a very big x of velocity in the x direction. On the other hand, you launch something at a low angle, like 20 degrees, it's probably moving forward very quickly, but it's not going to get very high into the air, and it will probably land a lot quicker. So is there a trade-off? Does one of those factors matter more than the other? That's what we're trying to discover. I can find the rest of these velocities by breaking my initial velocity vector into components. Initial velocity is 20 meters per second, and in this case, at 70 degrees. So I can find the initial velocity in the x direction, like my reference tables showed me, by multiplying the magnitude of the original vector by the cosine of the angle. So that's going to be 20 meters per second times the cosine of 70 degrees. And that gives me 6.84 meters. Since there's no acceleration in the x direction, we get the same thing for the final velocity in the x direction, 6.84 meters. In the y direction, we're going to take the magnitude of the original velocity vector, 20 meters per second, multiplied by the sine of that angle. That's going to be 18.79 meters per second. And the final velocity, when it's just about to land, will just have a negative sign in front of it, thanks to that rule we talked about earlier. Now I've got my whole table filled out. It's time to start using some equations. I want to find the final, the total distance traveled. Again, like I said, the first and third kinematics equations aren't really going to work here because your acceleration is 0, and they will both reduce down to some variation of the final velocity equals the initial velocity in the x direction, which is true, but it doesn't help us find the distance. Therefore, I'm going to use this equation. dx equals vix t plus 1/2 ax t squared. Since there's no acceleration, this whole term goes away. dx equals initial velocity in the x direction, 6.84 meters per second, times, we don't know the time. So that might look like a failure to you, but it's not. All that means is we just have to find the time first, and then we can find the distance in the x direction. How are we going to do that? We can use another one of the kinematics equations and the variables in the y direction. I'm going to use the fiat equation, Vf equals Vi plus At. So I know, and the way I'm going to do it this time is I'm going to say I know the velocity at the top is 0. So Vfy, that's just my final time. It doesn't have to be the exact, the ultimate final time. It just has to be after the initial, like these 2 points that we're looking at, final, initial. Final just has to be after the initial. So it could be at the peak of the ball's flight. It could also be when it goes back and hits the ground. So that's 0, initial velocity, 18.79 meters per second, plus a negative 9.81 meters per second squared, t. I'm going to move this to the other side. That becomes 18.79 with a negative, divided by 9.81. The time to get to the peak is 1.915 seconds, but remember, that's just the time to get to the peak. The total time must be that multiplied by 2. Times 2, and that's 3.83 seconds. I can take that 3.83 seconds, plug it in over here, and I should get the distance traveled in the x direction. About 26.2 meters. I'm going to do the same exact thing on the other side, but I'm going to be quiet. You can follow along, or you can pause it now and try it for yourself. So look at that. Now, I know I rounded a little bit on this side. I still did round a little bit on this side. So if you're watching real close to the calculator, you might say, well, you didn't really get the same thing. There were some rounding errors. If I hadn't rounded at all, I would have gotten the exact same number, okay? And that's what I got anyways. I get that both of them will go 26.2 meters. Now, that's very interesting, okay? Another thing, I'll come back to that in a second, but notice that there's some things that we didn't ever use. We didn't ever have to find the total height. Okay, it wasn't something that was relevant. We could have found it, but we didn't. It wasn't necessary. Going back to this, the fact that they both travel the same amount of distance, like I was explaining before, it kind of makes sense. The one launched at 70 degrees is in the air for a lot longer, but look at that initial velocity. Look at the velocity in the x direction. It's much lower than the velocity over here. On the other hand, whereas this horizontal velocity is higher, the total time that it's in the air for is lower. And if you'll notice, also, I used the other method for finding the time here. I used the launch speed at the launch speed and the landing speed instead of the launch speed and the speed at the very top and then multiplying by 2. Okay, we still got that this distance was the same. Those factors, one goes really high, so it's in the air for a long period of time, but moves slower in the x direction. The other one is not in the air for a lot of time, but moves faster in the x direction. Exactly trade off, and you get the same distance. This only happens in very certain special circumstances. The general rule is that two objects that are launched with the same initial velocity at the same time from the same place land in the same spot. In other words, they travel the same amount of distance if the angles that they're launched from are what we call complementary. That's a math word. You learned that back in math class. Complementary angles are angles that add up to 90 degrees, such as 70 and 20. So this would also work for 25 and 65 degrees. It wouldn't work for, let's say, 40 and 70 degrees because those don't add up to 90. Okay, so this only works if the angles are complementary. Another real quick interesting thing is that if you were to get these angles to start moving closer to one another so that they're more similar, so in other words, add one to here, subtract one to here, add one here, subtract one here, eventually they will meet at an angle of 45 degrees. And this is just another interesting fact. It turns out that a 45-degree launch angle will produce the biggest distance, horizontal distance that the object will travel. Okay, so if you want to launch something so that goes really far, you launch it at an angle of 45 degrees. That doesn't mean 45 degrees is always the answer to everything. If you want something to go really high in the air or stay in the air for a really long period of time, then you launch it at 90 degrees. But if you want something to move the farthest distance, you launch it at 45 degrees. That's pretty much it for projectile motion. There are lots of different questions on the homework. Hopefully you'll have a good amount of time to work through those in class. They can ask a multitude of different things, such as sometimes the horizontal distance, but sometimes it's just how much time is the object in the air for, or even what is the x component of the object's velocity. You really have to read the questions in order to understand. That's actually it for the kinematics unit. The next unit that we'll be talking about is forces, so I'll see you for that unit later on.